Okay, so here's a lot of important announcements here. So homework due Monday. I may make a slight change to that this afternoon, but probably not a huge change. But anyway, by tonight, that'll be finalized. Exam 2 is next Thursday. Many of you talked to me after exam 1. You said, oh, that didn't go as well as I hoped, or as I was thinking it would go. And so how can I improve my grade in the class? Exam 2 is how you can improve your grade in the class, and that means start studying this weekend. If your test was low on the first one, and you wait till Wednesday to study, I guarantee it's going to be low on the second one. You can't do this all in one sitting. You got to schedule out many times to sit down and work at this. So start this weekend. All the preparation materials are up. So if you go to Blackboard and you go to the exam prep right here, down the list, you'll see exam 2 folder. In exam 2 folder, whoa, where'd it go? In exam 2 folder, there's the outline. Every possible idea, concept, skill is on that's on the test, is on that outline. It's all things we emphasized in class. So that's like the centerpiece of your studying. It's that outline right there. Then, yesterday, I put up a big one giant web work set. It's something like 65 or 70 problems, okay? And you've got till Wednesday, 9 p.m. to do those for bonus credit on the exam. So depending on how much you do, you'll get some percentage added to your exam 2 score. Work on all of them. Try to get as many of them right as you can. This is a great way to study. You get immediate feedback. Okay? You'll either get 3 attempts per problem or 5 attempts per problem based on how many answers you have to put in. So if it's just like 1 or 2 answer boxes, most of those are 3. If it's got more answer boxes, most of those are 5 attempts. Okay, so keep track of that. But then after Wednesday at 9, that's the deadline for bonus because all the answers are posted. So you can go there and you can see the answers after that, so that's to help you study. Okay? And then I just have a quiz archive from a previous semester based on the exponential module 4. If you want more practice, that's all good practice. And of course, and then the videos, of course, are great to go back and review stuff that we talked about in class. So all the exam problems will specifically be about things we emphasized in class. I'm not asking you to go do research beyond that, okay? There's lots of things in here that we're not covering. But what the exam covers is what we emphasized in class. Don't forget the tutor room. ECA 216. Yeah, thank you. It used to be 216. Same hallway. All right, thanks. 225. Don't forget that. Open 5 days a week. You can go, study, work on your homework, and then there's people to help you. So in terms of help, myself and Roy are your very best resources, and this is the very best next resource you have. Any other tutoring on campus most likely will not be familiar with this. Their reference point will be what they've had in the past, which will be different than this. So we're doing our best to train the tutors in that room in this curriculum. So definitely your next best resource for help after myself and Roy. Okay? Videos. So the videos were getting really blurry and just not effective at all because they were so blurry. So I got in touch with the software and got some tech support. Now videos are, as long as you're on YouTube, as long as the quality is giving you a good quality on YouTube, the video should be crystal clear, okay? I'm actually glad that happened, that the videos were getting worse, because now I know how to make them excellent. So if you went to the video, so if you use the videos, great, keep using them. and you'll appreciate this. If you've gone in the past and you gave up on it because it was too blurry, go back and start now because they're good now. All right, next semester for Math 270, that's Calc 1. That's Calc 1. Would be the next course in the sequence. Many of you are engineers, right? So they're telling you 265. This definitely meets the requirement for 265. The reason I'm pointing out this to you, this is a special section of Math 270 that is, I've taught the last 3 semesters, including now, and then I'm going to be co-teaching it in the spring. And it's the approach is very different than any other calculus on campus, and it's very much in the same approach as what we've been doing, based on meanings, based on concepts, really forcing you to really understand things as the way to solve problems, rather than just kind of more procedural. Okay, so if you've enjoyed this and you feel like you're learning and you know you're going to take Calc 1, then this would be a great class for you. I highly recommend it. And like I said, it will absolutely take care of the 265 requirement. This version of Calc 1 takes care of any Calc 1 requirements that you could have. It's the I don't know how to say that, but it's the highest one. It'll any other Calc 1, if you have 270, it'll meet that requirement. Yes, sir.
For our exam 2, is that going to be in the PSH building once again?
Same procedure as the pretest and exam 1. Everything's the same on Thursday. Yeah. Sure. Other questions about stuff? So write that line number down when it's your turn to enroll. Get that course. And then there'll be a recitation also. It's much like this course. There's the Monday, Wednesday, Friday lecture, and then recitation. Any questions? Yeah? Yes, Thursday. Just like last time.
But it can't be Wednesday and Thursday.
Nope. Thursday. Other questions? All right. So I was walking towards the table last time. That's how we ended it. So that's how we're going to start it. So the time that this quantity, or independent quantity, is time since Mark started walking. And this is Mark's distance from the table. Two changing quantities that are changing together. And what do we call that? Changing quantities changing together. Covariation. This is really this understanding covariation is really what pre-calculus and calculus is all about. Understanding how quantities change together. Okay, so I'm going to do it. Here we go. Very exciting. Your teacher. Make this light full of himself. Okay, so time starts when I start walking, so time starts now, right? So it's not a very long distance to the desk, so I'm going to do that again. We're going to make it a chair. There we go. Okay. Need some more room. Ready, here we go. So time starts now. Feel like cool. I'll do it one more time. So it's distance from the chair. Distance from the chair. Ready? There we go. Time starts now. Okay. So, what did we say? In order to analyze the covariation, we take small equal changes of this. Oh, so for those watching the video, so what did I do? I started at some distance away from the chair, and then I started walking fast towards the chair, and then I slowed down until I got about halfway, and then at about halfway, I sped back up again until I reached the chair. Okay, so we're going to look at small changes in time, small equal changes in time. And then so for the first small change in time, we're going to ask. So first of all, at time equals 0, what was my distance from the chair? 0 or something else? Right, I was a distance away from the chair, so at time equals 0. I'm say here, okay? So I'm going to look at a small change in time. And in that small change of time, what happened to my distance from the chair? Did it increase? Did it stay the same? Or did it decrease? Decreased. It decreased a lot or a little? Relative to other changes. Yeah, so at first I took like a big kind of fast step, right? I took a big kind of first fast step. And then in the next equal segment of time, equal to that first one, what happened to my distance from the chair? Did it increase, stay the same, or decrease?
Decrease.
Did it decrease more or less than this? Less of a decrease. Okay? Next equal increment of time. Did my distance from the chair decrease again? Yeah, every time I do this, it gives me a point, right? So every time I look at the corresponding change in y, every time I look at the corresponding change in y for a small change in x, I get a point on the graph. Okay, I get a point on the green and black there. Okay, so now my third little change in time, my distance did what? Decreased. My distance continued to decrease. The amount of decrease, more or less than that? A little bit less. And so that pattern continued until I got to where? About halfway, right? So we'll do maybe 2 more. Oh. I can save it. Yes. Okay. And then next one. So what's happening to my changes in distance? What's happening to my changes in distance? That's what we want to know. In general, the changes in distance are doing what? Are they decreasing, the changes in distance? So let's talk this through. What about these changes? Are they negative changes or positive changes? Negative, right? So the changes in distance are negative. Okay? And are those negative changes getting more negative or less negative? More or less negative? Less negative, right? So I'm gonna would you agree that these numbers right here, are those numbers getting more negative or less negative? They're getting less negative, like our changes are, right? That sequence of numbers, is that an increasing sequence of numbers or a decreasing sequence of numbers? Increasing or decreasing? Those are increasing. Just like our changes are getting less negative. So when I asked you at first, I said, what is happening to those changes? You all said they're decreasing. But really, because they're negative changes, getting less negative, just like the sequence of numbers, getting less negative, the changes are increasing. This is very counterintuitive, and I'll show you why we need it in a second. The changes are increasing. In this part of the graph, the changes are increasing. Okay? The amount of distance that I covered, yes, decreasing. Those lines are shorter. The lines are getting shorter. So the amount of distance I covered each time was getting less and less. But because this quantity of distance from the table is defined, or distance from the chair is defined in that direction, and since that quantity was decreasing, smaller and smaller negative changes means relative to this quantity, that rate is, or those changes are increasing. So here, what's the rate of change doing? The rate of change of distance from the chair is increasing. Very difficult because your intuition says, oh, those lines are getting shorter. They're decreasing, so the rate is decreasing. But they're negative changes. And negative changes that get less negative, that's an increasing rate of change. Do you buy it? Yeah.
But that's only for negative, right? If it was doing the same thing going positive, those would still be increasing, right? Like if you were going down.
Okay.
Distance from the desk when you're walking away from it.
Okay.
If you're much faster, then your rate of change would increase, right?
Right. So my yeah. So let's do that. This is really good. We should do that. So I'm gonna change it. So we just did the first half, right? Okay. So now we're gonna do this. So ready? Time starts now. Okay. So what did I do? I slow down, and then I sped up this way. Okay? So let's do that. So at one point some point here these changes were getting less and less negative, and then at one point for a short period of time I didn't have any change at all, right? And then what happened? In the next change of time, did my distance from the chair increase, stay the same, or decrease? A little bit or a lot? A little bit at first. Next increment of time. Did my distance from the chair increase or decrease? Increased. More or less than the previous? More. So here, what was happening? Now, in the second half of the new walk, okay, my distance from the chair was increasing, and what were the changes doing? Changes were likewise increasing. So the question is, so here now the changes are positive. The changes are positive. Are they getting more positive or less positive? More positive. Is that increasing or decreasing? More positive. Better get that right? More positive means increasing. So notice the graph here. It's the best curve I've drawn all day. Okay? So over here, the rate of change, we said it's increasing. What's the shape of the graph? We talked about concavity. This is concave up, curved up. Okay? That corresponds, and so over here, we said over here that changes in D are positive. Getting more positive or less positive? More positive. Therefore, the changes are increasing or decreasing? Increasing. And therefore the rate is? The rate is increasing, decreasing, staying the same. Okay? And look, the rate of change is increasing. Concave up or concave down? Concave up. So this is why we make a big deal of this, saying that this rate is increasing and not decreasing, because this type of changing rate results in concave up, and concave up means the rate of change is increasing. So whenever the graph is concave up, your changes are either getting less negative or they're getting more positive, and that's always an increasing rate of change. Yeah?
And with concave down, that means decreasing.
What's decreasing?
The rate of change.
That's right. Concave down means that the changes are decreasing, and therefore the rate of change is decreasing, always for concave down. That's right. And that was actually, it's going to get too messy if I try to do it, but that was, so the second half of the walk, of the original walk, right? I was here, and what did I do? Like this, right? And so is my distance from the chair increasing or decreasing? Decreasing. Are the changes, so the changes are negative, do those changes get more negative or less negative? They get more negative or less negative? More negative. Those changes are getting more negative as I speed up towards the chair. More negative changes, is that an increasing or decreasing rate of change? So relative to my distance from the chair, can you see that my rate of change is decreasing? That's a decreasing rate of change relative to this quantity, distance from the chair. Decreasing rate of change. I'm speeding up, but relative to this quantity, distance from the chair, that's a decreasing rate of change. So you got to practice that because it's confusing. Your intuition, he's speeding up, that's an increasing rate, right? But the quantity is distance from the chair to your left. That's the distance from the chair, that way. Okay? So moving towards the chair means that if I speed up towards the chair, my rate is decreasing. My rate is decreasing. Getting more negative. The rate gets more negative. Got to practice that. Okay, so look on page. Anybody have a question? Page 188. Okay, so on page 188, I want you to fill in that table. And so, average rate of change. You'll have to kind of remember that. Maybe work together. That's that column over there on the right. So not only are you filling in the table, the columns for the changes, but then you're going to fill in the column for average rate of change. And you got to remember how you do that, what that means. And then when you're done with the question number 2, go on to question number 1 on page 189. Just the next page. So pages 188, 189, numbers 2, and then number 1. Can I erase what I wrote? Any questions? Okay, check your work on the rate of change of height in the bathtub. First thing, did you have negatives in the 2 right-hand columns? Very important. Remember, we talked first couple weeks of class. Changes can be negative, and what does that represent if a change is negative? It means something. What? Something different? What is it? Okay, so what does, when you have a change that's negative, so this is the change of the water height, if the change is negative, what does it mean? Caitlin, when the change is negative, in this case in the water height, what does that signify? What's that? Yeah, so what does that mean in terms of the water height? That is what? Increasing. So let's look. It was 50 before. Where are we? Hello. It was 50, and then it was 45.75. Yeah, so negative. So that's what we want to keep those negatives because it shows that the quantity is decreasing. The quantity is decreasing. Okay, so we look at these changes here, and we get -4, -7, -8, -9. So those changes are they increasing or decreasing changes? Are those increasing or decreasing changes? Decreasing changes. They're getting more negative. Okay? What about the rate of change? There's a problem here. What is the problem? With looking at this, before we looked at these and we said, oh, these are negative values, they're getting more negative. And since the changes are getting more negative, they're decreasing, and therefore the rate is decreasing. But there's a problem. What's the problem? You're shaking your head. And so how is that possible, that the changes are decreasing, but the rate of change is increasing? How is it possible?
Number of minutes elapsed is on a different scale each.
Right. What did we say about when we did it without numbers? We said we needed small, what? Equal changes of the independent variable. But these changes are not equal, right? So this is the advantage of what does average rate of change do? Average rate of change means the change per 1 minute elapsed. So it puts them on an even playing field, right? You can't compare these numbers because they're based on a different amount of independent change, of the number of minutes change. That's why we emphasized when we were drawing those graphs before, we need small equal changes in our independent variable, and then we compare the changes of the output. But if you've got different changes of your input, your average rate of change will take care of that because what are the units on this average rate of change? What will the units on that be? Yeah, per 1 minute. So this is change in height per change in time. So this is what? Centimeters per minute. So they're normalized to each other. They're numbers that you can compare to see what the rate is doing. So is the rate of change of water height increasing or decreasing? Is it increasing or decreasing? Jonathan's not here. Morgan, you just answered. So Penny, is the rate of change increasing or decreasing? Which one? Decreasing. Agree with that? Ollie? Increasing. Why increasing? Because the numbers go up. They're negative values and they're getting less negative. So these are, you got to really practice. This is an increasing list of numbers. Therefore, the rate of change is increasing. Here's the hard thing. Water is leaking out of this, or the height is doing what? It's slowing down. right? It's slowing down. But because we're talking about the height, and the height is decreasing, when you slow down the height, that's actually an increasing rate. It's actually an increasing rate of change. Lorenzo? So the speed is decreasing. If you're going to say decreasing, you got to say the speed of the height of the water. That's decreasing. How fast it's going down. Okay? But the rate of change of the height of the water is actually increasing because those changes, the rate of change is becoming less and less negative. All right, and it all goes back to concavity of the graph. If we were to graph this of time and water height, what would that graph look like? First of all, would it be going up or down? Be going down. Would it be concave up? Would it be straight or concave down? It'd be concave up. Okay, that's what this graph is going to look like. And so those rates, it starts off, the average rate starts out at a high negative, and then it gets less negative, and then even less negative, and less negative. So that's an increasing rate, and therefore the graph is concave up. Increasing rate of change means concave up. You got to practice it. So you'll have homework to keep practicing that. All right, how about number 1? Any questions on that? Let's just get right to the graph here. Let's get right to the graph. Okay, so you found an average rate of change from 0 to 0.5. What average rate did you find for that? Anyone find that yet? So from there to there, an average rate of change is the constant rate that's going to see the same change in height for the same change in time. Did anyone get that constant rate? What is it? It's not a negative rate. That's a positive rate of change. It's going to be 20 over 40. 40 is that first average rate, feet per second. So then now from 0.5 to 1, so you got to imagine like a straight, the average rate of change is going to be like the straight version of the curve, right? It's going to be the constant rate that's going to see the same height for the same change in time. And what's that one? 24. Next half second. Average rate of change, the constant rate to see the same change in height for the same change in time. And then? Am I always going two? Yeah, I'm just going 2 lines every time. Boom. So imagine we're turning this curve into a bunch of straight lines, a bunch of constant rates over half-second intervals. Each constant rate is the constant rate to achieve the same change in height over the same time interval. That's average rate of change. What are the numbers? One more. Nice and loud. Is that the last one? Oh, okay. All right. So, in the first 1.5 seconds, what's the height doing? Is the height increasing or decreasing? Increasing. That means the changes are positive or negative? Positive. More positive or less positive? Becoming less positive. Changes are becoming, or average rate of change. Our average rate is becoming less positive. Therefore, the rate of change, increasing or decreasing? The average rate is becoming less positive. Is that a decreasing or increasing rate? Decreasing. Okay, over here. Average rate. What's it becoming? More or less positive or negative? Becoming more negative. Right? Therefore, values that become more negative. Increasing or decreasing rate of change? It's speeding up, so it's increasing rate of change, right? No. The changes become more negative. Now that thing is decreasing, and so if changes become more negative, then the rate of change is still decreasing. And because the rate of change is always decreasing, the graph is always... So the rate of change is decreasing here, and the rate of change is decreasing here. Concave down everywhere. Both when the changes become less positive and when the changes become more negative. Relative to up being positive, the rate is always decreasing when you throw something in the air. If up is positive, it's slowing down, it's speeding up, that's a negative rate of change, always. Even though it's speeding up as it goes down, it's a negative rate of change. And that's why the graph is always concave down. Because concave down associates with decreasing rate. Questions on this? Okay, let's talk about polynomials. So polynomials are the types of functions that have these characteristics. They increase, they decrease, right? They have concave up, concave down. So let's look at those. So polynomial is a function with input x, and it's the sum of monomials with whole number exponents and real coefficients. So here's two examples. So sum obviously means we're adding together a bunch of things, all right? And each of those is called a monomial. All right, the exponents are whole numbers. If it's a polynomial, you got to have a whole number for your exponent. This is like x to the 0, because x to the 0 is 1. So it's like if you just have a constant value, it's like x to the 0. Those are all whole number exponents. You can't have a fraction other than a whole number. So you can't have a decimal exponent. You can't have a negative exponent. Only whole numbers. Okay, but the coefficients, the multipliers out in front, can be any real number. -3, 10.5, pi, -9, 11/4. Any real values are okay for the coefficients. So let's look at a monomial here. This is 10.5 x to the 5th. That's a monomial, single term, like that. Is it exponential growth? Is it exponential growth? Yes or no? 10x to the 5th. Some are nodding saying yes. Anyone say no? So we spent a month, almost a month, learning the very specific type of growth that exponential growth is. Is this exponential growth? What's our form for exponential growth? A, B to the x. Same type of growth? What does the input mean in exponential growth? What does the input mean? What is it? Say it. Someone say it. That you do what? By? What is that? That's right. It's the number of times you multiply by. That's what an exponent is. The number of times you multiply by the growth factor. What's the input over here in the monomial? Yeah, it's what you multiply by. It's the base. And so this says take the input and do what to it? Multiply the input together 5 times. Same type of function or different? Totally different. Totally different. Exponential growth is a very specific type of growth. As we increase the input, we keep multiplying by more and more growth factors. Over here, as we increase the input, we just keep taking the input to the 5th power every time. Totally different. Okay? Again, exponential growth is a very, very specific type of growth. When you see a curve, chances are it's not exponential growth. There's a zillion types of curves that we could have as in covariation. Exponential growth is a very specific type of curve. Monomial is a different, very specific type of curve. Okay? Totally different. The input here is how many times we multiply by the growth factor. Here it's what number gets multiplied 5 times together to get your output. Okay, so the so there's 2 forms. This definition is talking about the expanded form with our real coefficients and our whole number exponents. This is the factor form. Some polynomials can be factored into this form here, that if you multiplied it back out, it would look like this. Okay, we're going to talk about that next week. Well, let's talk about the expanded form. What does the expanded form help us to determine about the graph or the relationship? There's something very quickly we can get right away from the expanded form.
That how many curves have changed over graph?
Yeah, that's one thing we can get. We're not going to talk about that, but yes, you're right.
We can determine whether it's concave up or concave.
Oh no, it's going to change. So something like this, the concavity is going to change several times. So it's something real simple and quick we can get about the graph. Nathan? Okay. But yeah, the degree, but then what? But what about the graph? What can we get from this? Okay, we can get the y-intercept. What's equal to 0 on the y-intercept? Y, right? Y is equal to 0. What's the y-intercept of this one? 11/4. And y equals 0 on the y-intercept. That should feel uncomfortable. It's not true. What's equal to 0? X, right? So we're not going to the left or the right. We're here, the y-axis is where y equals 0. So the y-intercept is that y value where x equals 0. In this case, for this one, f of x, it's 11/4. If you plug x equals 0 into the function, it's going to give you 11/4 because all those monomials become 0. Okay, the other thing that it helps us with is what's called end behavior. End behavior, we're just talking about end meaning the ends of the graph. Okay, so way out on the right end of the graph and way out on the left end of the graph. So we're talking about when we say end behavior. Okay, so the way out on the right end is when x values get really, really large. And so we represent it this way, x. So here's our axes. If we're talking about the far right end, we're saying as far right as you can imagine. Over here. And further, okay? So this is x increasing without bound, or x going to infinity. It's not the greatest language, but it's the most common. It's really better is to say x is going to increase without bound. And so that represents the far right side of our graph. And similarly, x is going to get as large as you can imagine negative. And that's going to represent what's happening on the left side of the graph. And what we mean by that is one of 2 things can happen. Y can go up to positive infinity, or increase without bound positive, or y can, in these polynomials, those are the only 2 things that can happen. So on the right end, you have 2 possibilities. Y goes to positive infinity, or y goes to negative infinity. Similarly, on the left end, there's 2 possibilities. Y goes to positive, or y goes to negative infinity. I need to do a little bit more, sorry. Can you give me 2 minutes? I'll give it back to you another day. Okay, so these are the possibilities. On the right end, as x goes to positive infinity, we can go up or we can go down. And on the left end, two possibilities. The function can go up or it can go down. All right? So how do we determine that? So suppose x, talking about x getting really big, suppose x is 17,000. Is that big? Nah, it's not big. How about 17 million? No, 17 billion. That's kind of big, but 17 trillion, now we're starting to get there, okay? Starting to get large. Okay, why did I pick 17 trillion? Okay, why? Because we in trouble. And if you don't know what I mean, find out, okay? All right, so 17 trillion. I'm going to put 17 trillion into here. What is that going to tell me to do with 17 trillion? And what is it going to tell me there? Okay, so now, compare those two. 17 trillion to the 6th, 17 trillion to the 5th. Those are both fairly large numbers, okay? But compare them to each other. How does 17 trillion to the 6th compare to 17 trillion to the 5th? So it's 1 greater, right? Because 6 is 1 greater than 5. So it's 1 greater. What is it? 17 trillion times, how many zeros is that? 12? This one is 17 trillion times greater than this one. Do you see? Because I multiply it by 17 trillion one more time than this. So this looks like 0 compared to this because 17 trillion is so big. So even though that's a huge number, it looks like 0 compared to this one. So when x gets very, very large, all these lower powers, video's done, all these lower powers are like 0 for very large x compared to what's called the leading term. The leading term has the highest power of x, and it takes over for very large values of x because of what we just talked about. So the end behavior of this polynomial is the same as the end behavior of the leading term. So whatever the leading term, whatever that monomial does at the ends, is what that whole polynomial is going to do at the ends. So to find the end behavior, you just determine the end behavior of the leading term. And you got the end behavior of your polynomial.
This one's still up, right?
Say it again?
This one's still up, right? This,
No, negative x to the 6th. We'll double down. Negative x to the 6th will do this.